Pressure, volume, temperature. How are these variables related? Hello, SciPals! I am Sir Senan Salubayba, your science teacher for today. In this episode of Agham Alam Hub, we are going to explain the relationship between gas pressure and volume at constant temperature. We will solve a mathematical problem involving the Boyle's law. We will also demonstrate the relationship between gas pressure and volume at constant temperature through a simple experiment. Furthermore, we will appreciate the importance of the Boyle's law in real-life situations. In the next few minutes, we will explore science for another moment. Remember that gas is a state of matter that does not possess any definite volume or shape. They totally fill all the space accessible to them. The characteristic or property of gases to fill the available volume within a container is the result of the freedom that gas particles have to move everywhere in the accessible space. Scientists observed the relationships among the properties of gases, which led to the formulation of the different gas laws. The relationship of volume and pressure of gases is one of the gas laws called Boyle's law, after the Irish scientist Robert Boyle. The Boyle's law states that the volume of a confined dry gas varies inversely with the pressure applied on it, provided the temperature remains the same. If we put the relationship of volume and pressure into mathematical equation, we obtain P varies 1 over V, where the symbol alpha is a sign that means varies with. Then, the pressure is equal to constant divided by volume, or the product of pressure and volume is equal to constant. In this equation, P is the pressure and V is the volume. The K is a constant that takes into account the number of molecules and the temperature. Thus, pressure varies inversely with a change in volume. Experiments are often carried out at room temperature and pressure. Since the temperature and atmospheric pressure vary from day to day, experimental results cannot be compared easily. It is desirable, therefore, to adjust all results mathematically to standard conditions. If P sub 1 is measured as initial pressure and V sub 1 is measured as initial volume, P sub 2 is the final pressure and V sub 2 is the final volume at a standard atmospheric pressure, then initial volume is equal to constant divided by initial pressure and final volume is equal to constant divided by final pressure. Let us try applying this equation into a simple mathematical problem. If 100 ml of hydrogen gas was collected at 760 mm of mercury, what is the new volume of gas when the barometer reads 745 mm of mercury at the same temperature? In the given problem, what is the initial pressure? Right! The initial pressure is 760 mm of mercury. How about the final pressure? Correct! The final pressure is 745 mm of mercury. What does the 100 ml of hydrogen gas represent? Right! It represents the initial volume of the gas. Using the given data, let us now solve the final volume of the hydrogen gas in the sample. From our formula, the product of initial pressure and initial volume is equal to the product of final pressure and final volume. Since the final volume is unknown, the formula will be final volume is equal to the product of initial pressure and initial volume divided by final pressure. Substituting the given values, we will get final volume equals 100 ml multiplied by 760 mm divided by 745 mm. Therefore, the final volume is 102 ml. Let us now demonstrate the concept of the Boyle's law using this setup. In this setup, the other end of the syringe is sealed so that air is trapped inside. Let us look at the reading of the volume of air inside the syringe. Adding a set of weights above the syringe means increasing the pressure applied to it. What do you think will happen to the volume of air inside the syringe if we put 500 grams on top of the plunger? That's right, the volume decreased. From the initial volume of 10 ml, the volume of air inside the syringe is now 8.5 ml. Now let us see how we use Boyle's law in our daily life. The principles involved in some household technologies like liquefied petroleum gas cylinders and oxygen tanks can be explained in terms of the gas laws. Liquefied petroleum gas is also known as battle gas. It is used in cooking, heating, and even lighting, especially in rural areas where there is no electricity. It is a fuel made up of propane and butane and comes from the processing of petroleum. The highly volatile gases are converted to liquid form by placing them under pressure. At normal atmospheric pressure and temperature, propane and butane exist as gases. Oxygen tanks are used to store gas for medical breathing, at medical facilities, and at home breathing at altitude in aviation, either in a decompression emergency or constantly oxygen first aid kits. Oxygen therapy gas blending for creating diving breathing mixes such as nitrox, trimex, and heliox. In this episode of Agham Alam Hub, you learned the relationship between gas pressure and volume at constant temperature. Volume is inversely proportional to pressure. A decrease in pressure means an increase in volume. In solving mathematical problems involving the Boyle's law, we use the formula P sub 1 V sub 1 is equal to P sub 2 V sub 2, wherein the product of the initial pressure and initial volume is equal to the product of final pressure and final volume. Real-life applications of the Boyle's law include the liquefied petroleum gas and oxygen tank. LPG is useful in immediate needs such as cooking and heating, or even lighting in some rural areas where there is no electricity. Oxygen tanks are used to store gas for medical breathing at medical facilities and at home breathing at altitude in aviation, either in the compression emergency or constantly oxygen first aid kits. Oxygen therapy gas blending for creating diving breathing mixes such as nitrox, trimex, and heliox. That's all for today, SciPals. Don't forget to like, share, subscribe, and turn on the notification bell. See you again next week for another moment Only here in Agham Alam Hub, Palajan SciTech Portal. Bye!